Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Analyze reaction 1. C2FClBrI with H2Ne, hydrogenolysis hydrogenation context. Here C2FClBrI represents a 2-carbon compound with 1 F, 1 Cl, 1 Br and 1 I substituent total on 2 carbons, formula C2H, X, FClBrI. Since the formula C2FClBrI implies a dihalocarbon framework, we interpret this as all structural isomers of C2FClBrI, saturated, 2 carbons with F, Cl, Br, I distributed on the 2 carbons. The 2 carbon atoms must collectively bear F, Cl, Br, I plus enough H to satisfy valence. Total substituents on 2 carbons, each tetravalent, we have 4 halogens, F, Cl, Br, I, for 2 carbons giving 8 bonding slots minus 2 for C to C bond is equal to 6 remaining, with 4 halogens that leaves 2 H atoms, so formula is C2H2FClBrI. The possible structural isomers, ignoring stereoisomers, are based on how the 4 halogens are distributed between C1 and C2. Distributions are 4, 0, 3, 1, 2, 2. 4, 0, 1 carbon bears all 4 halogens, impossible since carbon is tetravalent and already has C to C bond, so max 3 halogens on 1 carbon. 3. 1 C1 has 3 halogens and C2 has 1 halogen plus 2H. Choosing 3 from F, Cl, Br, I, for C1 gives C, 4, 3 is equal to 4 ways, leaving out F, or Cl, or Br, or I on C2. Each gives a distinct structural isomer since the single halogen on C2 differs. That gives 4 isomers. 2 to C1 has 2 halogens, C2 has 2 halogens, each with 1 H. Number of ways to split 4 halogens into 2 plus 2 is equal to C, 4, 2, 2 is equal to 3, dividing by 2 because C1 and C2 are distinguishable only if we consider the molecule, but actually since the 2 carbons are different ones substituted differently, we get C, 4, 2 is equal to 6 but pairs, AB vertical bar CD, and CD vertical bar AB, represent the same compound only if the molecule is symmetric, which here means same set on both carbons. C, 4, 2 is equal to 6 ordered, but F, Cl on C1 Br, I on C2 is different from Br, I on C1 F, Cl on C2, only if we can distinguish C1 from C2 since each carbon has different substituents in asymmetric cases they are the same compound. So unique combinations is equal to C, 4, 2, 2 is equal to 3. Total structural isomers of C2H2FClBrI is equal to 4 plus 3 equals 7. Upon hydrogenation with H2Ne, all halogens are replaced. No, H2Ne does not typically remove halogens. This reaction replaces the CX bonds. Actually, rereading, H2Ne can hydrogenolyze C halogen bonds replacing halogens with H. All halogens are removed giving C2H6, ethane, as the only product regardless of which isomer. So A is equal to 1 product, ethane. Moving on to the next step. Analyze reaction 2 C4H8 alkene isomers with H2Ne. All structural isomers of C4H8 that are alkenes, excluding stereoisomers 1-butene, CH2 is equal to CH to CH3, to butene, CH3CH is equal to CH3, isobutylene to methylpropene, CH3, to C is equal to CH2, cyclobutane is not an alkene, methylcyclopropane is a cyclocane not alkene. Weight, C4H8 cyclic compounds. Cyclobutane and methylcyclopropane are cycloalkanes with formula C4H8 but these are not alkenes. The alkene isomers of C4H8 are 1-butene, 2-butene, cis and trans, but excluding stereoisomers is equal to 1 compound, 2-methylpropene. That gives 3 alkene structural isomers. Upon hydrogenation, 1-butene, butane, 2-butene, butane, 2-methylpropene, 2-methylpropane, isobutane. So products B, butane, N-butane, and 2-methylpropane, isobutane is equal to 2 distinct products. But wait, if we also include cyclic C4H8 alkenes. Cyclobutene, a cyclic alkene, C4H6, no, cyclobutene is C4H6. Actually methylencyclopropane is C4H6 too. The cyclic C4H8 structures with a double bond, there are none that are simple monocyclic alkenes with formula C4H8 other than what's listed, since cyclopentene would be C5H8. So B is equal to 2 products, N-butane and isobutane. That gives A plus B is equal to 1 plus 2 equals 3, not 5. Moving on to the next step. Reconsider. Perhaps H2 here means only one equivalent of H2 is added, hydrogenation of double bond only, not hydrogenolysis of halogens. For reaction 1, adding H2 across C is equal to C. But C2FClBrI may contain a double bond. If C2FClBrI is a 2-carbon compound with a double bond, C2FClBrI with degree of unsaturation is equal to 1, double bond, formula C2FClBrI means exactly FClBr, ion 2 carbons with a double bond. Each carbon in C is equal to C has 2 remaining bonds. So one carbon has 2 of the 4 halogens, and the other has the remaining 2. The isomers distribution of FClBr I as 2 plus 2 on each carbon of the double bond. Unique isomers, excluding stereoisomers, FCl is equal to Br I, F, Br is equal to Cl, I, F, I is equal to Cl, Br. Since the 2 carbons of a double bond are distinguishable, different substituents, but UB vertical bar CD versus CD vertical bar UB, if both carbons have different pairs they are the same compound, just flip. So 3 structural isomers. Upon adding H2, each gives CHFCl type products. Products A from each isomer, A, CHFCH, B, CHFBrCHCli, C, CHFICHClBr. These are 3 distinct constitutional products, excluding stereoisomers. So A is equal to 3. And for the final step. For B, C4H8 alkene isomers, hydrogenation products. Structural isomers of C4H8 alkenes, excluding stereoisomers 1-butene, 2-butene, 2-methylpropene is equal to 3 alkenes. Products 1-butene, N-butane, 2-butene, N-butane, 2-methylpropene, isobutane. Distinct products B is equal to 2, N-butane, isobutane. A plus B is equal to 3 plus 2 equals 5. This matches the given answer. Therefore, the correct answer is A plus B is equal to 5. The correct answer is shown on screen.